Honors Chemistry, and welcome to a brief discussion. I think it's brief, and discussion. We use the word loosely because I'm talking to myself, but it's an asynchronous period, and this is a way to make sure the information gets conveyed, even though we aren't all talking together. So anyway, let's talk a little bit about some of these concepts from your molarity unit that you were supposed to pick up on last night. So first, macroscopically, right? And again, macro means... right, large scale, visible to the eye. So macroscopically, what is a solution? What are some ways we can describe a solution? Okay, we could use things like homogeneous mixture. We could use things like one solute dissolved in a solvent, right? Where the solvent is the thing that is present at higher concentration, right? Though typically when we're talking about aqueous solutions, we just mean the water, right? Do be mindful, it is assumed you know all these things, so what I would do is I would layer all these things into my outline. If you don't care for your class notes to be in with your reading and lecture notes, you are welcome to go ahead and print a copy of these. You can print these as a PDF if you look at your options on Jamboard, if you think that would be helpful to you, or you can just take notes on a sheet of paper. We are going to do some practice problems together also, so whatever works for you. All right, microscopically, right, meaning not with our eyeballs, what is a solution, right? So again, we have a solute and a solvent, but at the particle level, right, what must be true about a solute and a solvent if they're going to form a homogeneous mixture? Right, the solute and the solvent must be similar, right? And when you go back to middle school science, right, you guys talk about things being polar and nonpolar, right? You guys talk about how water is very polar. So in order for one thing to dissolve in another, they must be similar in polarity, right? So something that's decidedly nonpolar, like, I don't know, oil, for example, right, does not dissolve in something that is decidedly polar, like water, for example, right? So when we talk about the fact that water and oil don't mix, right, the layering, the fact that they don't mix, is due to the fact they are different in polarity, right? Two different, right? The fact that oil sits on top of water has to do with their densities, right? Not all substances would sit on top of water, right? Where it would sit would depend on its density, right? All right. Next up, and then in terms of microscopically, right, in order to get something to dissolve, right, we have to think about all the forces at play, right? We have a solute attraction. We have a solvent attraction, right? Those are the forces that hold the molecules next to its neighboring molecule when they have a sample of just itself, right? But then we have to take into account if they're going to mix together, there needs to be a significant solute-solvent attraction such that they would leave their other partners. Yes, does that make sense, right? Like the solute-solvent attraction must be strong enough that it is a more beneficial pairing, right? Or energetically more beneficial pairing than what it was attached to previously. All right, so thinking about solubility, where when we say solubility, what are we really talking about? Right, we're talking about the amount of solute that can dissolve in this case, water, right? What is it that we can do to increase the solubility of sucrose or any solid solute in water? Right, we can increase the temperature, right? If we increase the temperature, the solubility will go up of that substance, right? Which is why, for example, going back to life things you should know, right? When you're making a lemonade or sweet tea or something like that, right? The sugar will dissolve much better if the water is heated, right? Versus if you try to dissolve everything into cold water, right? Next, how can we distinguish between aqueous sucrose and aqueous sodium chloride? I'm sure that for some of you guys, the immediate answer is like, well, they would taste different, which is true. They would, right? But if we were just looking with our eyeballs, they would look exactly the same. So if they look the same, what are some other options that are lab safe, right? Because taste is not one of those, right? We could do what? Right. We could assess whether or not one is an electrolyte solution or not, right? Meaning we could test the conductivity, right? This sodium chloride is an electrolyte, specifically a strong electrolyte, meaning it dissociates completely into its ions, yes? Meaning that when I look at a sample of aqueous sodium chloride, I don't have sodium chloride particles, I have sodium ions and chloride ions floating around in the water. Whereas when I have an aqueous sucrose solution, I still have molecules of sucrose that are interacting with the water. Yes, no ionization, which means no conductivity, in a sucrose, none or very low conductivity in a sucrose solution, excellent conductivity in a sodium chloride solution. We could also do other methods, right? For example, you guys are all super great with solubility rules, and we could apply some solubility experiments here also, okay? Life examples of gas dissolved in water. So your book goes through a couple examples, like the fact that if we were to, say, boil water, we would see small bubbles before we ever reach the boiling point, and those bubbles would accumulate on the sides of the glass. Same thing when you fill a glass of water from the sink. But in addition, what else is there? Right. Fish. Yes, fish are a great example. Because what do their gills do? Right, their gills filter out dissolved oxygen from the water, right? That is exactly what they're doing. Note that the gills are not doing some weird chemical reaction where they break down water into oxygen, right? That's not what we are saying, right? We are saying that they are filtering dissolved oxygen from that water, right? That's what gills do, which is why surface area is so important, right, for gills. How can we increase the solubility of gases in water? And note that they are their own separate thing because it's a different method, right? So we could, one, decrease the temperature, which goes back to that soda example in your guys' book, right? And like if you've never tried a cold carbonated beverage next to a warm carbonated beverage, try it, right? If you have some sodas at home, put one in the fridge, leave one out. And when the one in the fridge is very cold, go ahead and taste them and check the difference, right? But if we get more of that carbon dioxide to dissolve, then that also means more opportunity, right, for acid to be produced because CO2 plus H2O does make some carbonic acid, right? And it leads to a different flavor profile and mouthfeel when you taste it, okay? In addition, we can increase the pressure of the gas, right? So whatever the gaseous solute is, we could increase the pressure of it above the water and more of it will dissolve. Okay, now let's go ahead and do a few practice problems together. Right, so you do want to make sure you work these with me, right? And you might find these helpful later. So let's say that a chemist wants to make 2.5 liters, so that is a volume of 0.1 molar KCl solution, right? Where that M is our concentration and it stands for molar or molarity. And we should always stop and translate it, right? It means that there are 0.100 moles of KCl solute equal to every 1 liter of KCl aqueous. I'm going to put the aqueous in just a minute. But that's what it means. And so just like we did when we started with density, we should stop and write out that it's a conversion factor. Now, it says that we're looking for the mass in grams. That's our goal, which means that our given is clearly right, that 2.5 liter volume, because we've already decided that that molarity is a conversion factor. So we'll start with our 2.5 liters of KCl, and then we will set up a conversion factor to get from our aqueous KCl to moles of KCl, which means that we'll use our molarity. So we'll go from our liters of aqueous KCl to moles of KCl solute. And then how do we get from moles to grams? Right, using the molar mass of KCl. And once we get that, then it's just a matter of typing it into the calculator correctly and making sure we do that math part. And if we do, we end up with 18 point something, which means rounded to 2 sig figs, courtesy of that 2.5, we are going to get 19 grams of potassium chloride. Now, let's talk about how we use this information to actually make this KCl solution. So we start with a volumetric flask. Well, first we need our mass, right? So we have 19 grams of KCl are necessary to make 2.5 liters of 0.1 molar KCl solution. So one, we'll take our volumetric flask and we'll fill it with some water, right? How much doesn't really matter, just needs to be less than 2.5 liters. Then we'll add in our 19 grams of KCl, and then we will swirl to dissolve that KCl, right? Once we have dissolved the KCl in the water that's in there, we will top off the flask with water to the 2.5 liter mark, right? And then we will have our solution. Okay, next problem. It says that how many liters, so our question or our goal is volume in liters, 0.5 molar sucrose. So again, let's go ahead and translate this into its actual pieces. So that means there are 0.5 moles of our C12H22O11 equal to every 1 liter of C12, H22, O11 aqueous, right? And it says that contains 1.5 kilograms of sucrose. So that's clearly our given because the molarities are conversion. So we'll start with our mass of sucrose, so 1.5 kilograms of sucrose. Obviously, step 1 is we're going to have to get from kilograms of sucrose to, right, grams of sucrose, and that will be step 1. And once we've converted from kilograms to grams of sucrose, now that we have a mass of our solute, now we need to go from a mass to a moles, right? Because molarity is the relationship between moles and liters, so we need to get our grams into something we can use with that conversion factor. So we'll take our grams and we will convert it into moles using the molar mass of sucrose. And then we can employ our molarity. Oh, not 1, but 0.5 moles of sucrose are equal to every 1 liter of aqueous sucrose. And then it's just a matter of, again, making sure we type in all the math correctly and we put our exponents in correctly, all that good stuff. And then we come up with a final answer of 8.8 liters, bearing in mind we need 2 significant figures based off of that 1.5 kilograms of sucrose. Right, and next problem. It says that we are going to determine the concentration of, note, chloride ion in 0.15 molar NaCl. Again, translated, that means 0.15 moles of NaCl solute equal to 1 liter of NaCl aqueous. Now, we also know that if we want to talk about chloride ion, we need to break down our NaCl, right? So 1 mole of sodium chloride is equal to 1 mole of chloride ion, right? That's stuff we've been talking about since chapter 5. So now we're just going to take our, and this is kind of like a two-piece, like when we convert miles per hour, right? That's basically what we're doing, right? We're going to take our moles per liter, our moles of NaCl per liter of NaCl aqueous, and we're going to take our moles of NaCl and convert that to moles of chloride ion. So now moles of NaCl cancel, and we are left with moles of chloride ion per liters of sodium chloride solution, right? And it's moles per liter here, but we can go ahead and then write that out as a molarity, right? So that would give us 0.15 molar, capital M, chloride ion. What this says is that 0.15 molar NaCl contains or is equal to 0.15 molar chloride ion, right? Obviously, we could say that 0.15 molar sodium chloride is also equal to 0.15 molar sodium ion, right? That's the whole point of what it means to say that something dissociates into its respective ions. Yes? All right, next problem. So let's read the problem. So it says that we have 122 milliliter, so that's a volume, sample of 1.2 molar sucrose solution is diluted, right? That diluted is key, right? Because that tells us this problem is a dilution. So we should scroll through our memories, right? And pick out the tidbit that applies to a dilution, right? Which means M1V1 equals M2V2, right? So let's go ahead and take this problem and translate it into the pieces that we need to apply that equation. So 102 milliliters of 1.2 molar sucrose is diluted to, right? So that means the new condition, to 500 milliliters of some unknown molarity, right? So that new molarity is our unknown, right? And so we can look at this as that diluted is where that equals sign comes in, right? We have our M1V1 and then diluted separates that from our M2V2, right? So we have 122 mils of 1.2 molar is equal to 500 mils of unknown molarity. And then we just need to solve for molarity using all the algebra skills we have accumulated over time. Now, do be mindful here, the molarities and the volumes simply need to match across the equal sign. So we could have liters and liters or mils and mils, right? And that would be fine. We could have molar and molar or millimolar and millimolar, and that would be okay also. All right, now we have a final answer, which we're going to round to the correct number of significant figures, which is 0.29 molar sucrose, courtesy of that 1.2 molar being only 2 sig figs. All right, now, the thing about dilutions is we need to bear in mind what changes and what doesn't. When we take that 122 mils of 1.2 molar, there is a fixed number of moles there, right? The moles do not change, right? However many moles are present are the moles that came from that 122 mils of 1.2 molar sucrose solution. The only thing we're doing is adding a boatload of water to that, right? And that's what makes a dilution a dilution. Okay, and practice, practice, practice. So here are your Chapter 13 EOCs to work on. And the little tidbit that's due for tomorrow, I do believe you should be able to finish those EOCs during the course of class and work on that last section for homework. All right, be good, have a lovely day, and I will see you soon. Bye, guys.